Hello and welcome to our discussion of minerals. In this segment we'll be talking primarily about how minerals are put together. We'll be talking a little bit about chemistry and bonding, and we'll give a short overview of those. And we'll talk about how minerals are classified both based on their geochemistry and based on their mineral structure. In general, in minerals, and when we talk about them in this course, are going to be important both as environmental hazards that are concerns both because we need to be cleaning them up, either because of as mineral resources we were extracting them and leaving behind waste, or leaving behind conditions that exposed minerals to weathering and acidification. Alternatively, they are materials that we've concentrated in our environmental conditions, within an urban environment, such as, say, asbestos, for instance, which we find in many different kinds of buildings. Also, we find different kinds of materials in the past have been used from minerals that maybe have been radioactive, that shouldn't have been used, and those kinds of wastes are still around, and something to be concerned about. In general, if we think about the materials that we use in everyday life, either we have to grow materials, fibers, for instance, to make cotton, to weave cotton and to make certain kinds of linens. Silk would be an example as well. That's organically produced. Hemp would be an example as well. That could be woven into something. If you're wearing anything with leather, obviously leather is a natural material that's been tanned and modified. The other side of this coin is that if we cannot grow it either as plant or animal material, then we have to extract it from the Earth's interior. And we see in my initial list here just a few things that we are interested in, ranging from the somewhat obscure coltan down here at the bottom, which is a mixture of two minerals, columbite and tantalite, and those contain rare earth elements, or what I'm labeling here as REEs. You can see them down here at the bottom. REEs are rare earth elements. And going into electronics, high temperature capacitors, various color things in televisions and even automobiles. We have things like gold. Gold is a mineral, believe it or not. It's what we call a native element. It exists both, in some cases, in minerals, but as a mineral itself. Right? By itself, it will exist naturally. And computer circuitry, scientific instruments, these are common, as well as it has a decorative and an economic value as well that kind of exceeds other economic minerals. Because gold is such a high price, we can store it as a way of kind of storing economic value reservoir. You can take a lot of coltan to equal the same amount of the value of a 1 pound bar of gold. Other things that we might be less familiar with, ceramics have natural earth materials in them, in particular clay. Kaolinite is an example. Alkali elements are used to make soap detergents, and then obvious things would be things like copper or zinc or lead, which go into plumbing, electrical components. And other things of relevance here are some very famous gemstones. We look to minerals as the source of birthstones, for example. If you are familiar with your month of birth, you can look up a particular stone. On the right we have diamond, which is the Hope Diamond. That's in the Smithsonian. And one of the equally large chalk emeralds. You can see here I have carat listed. Okay? Carat's actually just a weight in grams. Okay? It's a fraction. 1 carat is a fraction of a gram, and so these are pretty big carat weights here. 45 carat weights is a big diamond, but actual mass is pretty small. Down here we have the Star of India as an example of a sapphire, and then the emerald here. All of these have natural examples that are of little or no value. Sapphire is essentially the mineral we call corundum. Sapphire is the gem variety of that. Emerald's equivalent is beryl. Diamond doesn't have an equivalent mineral name. Diamond is just diamond, but there are industrial grade diamonds which lack the carat weight, the color, the clarity, and the cut to become or to be of any significant value as jewelry. Okay? All of these things are minerals that we're interested in thinking about how they're organized. To kind of understand that, we want to review a little bit about the atomic components and atomic structure. Right? This is going to help us understand a little bit more about how minerals are put together. Right? So here are two models for the atom. The one on the left shows the nucleus, and then it shows a cloud around the nucleus, which contains the electrons. Within the nucleus, we have protons, which have a positive charge, and the neutrons, which have no charge. It sounds like they should be negative, negative. They're not. Neutrons are neutral, zero charge, as I've shown you down here on the bottom right-hand side. So this cloud doesn't show us where the electrons are. It just shows us that they exist somewhere in this field. And all atoms, like any solid material or structure, have a radius. Right? They have a size, and that size dictates where they'll fit into a mineral and how they're arranged in a mineral. And I'll talk a little bit more about that later. On the right, we see a slightly different model, and that model shows us electron shells or electron orbitals. In this case, for every proton that's in the nucleus, we expect there to be an electron somewhere out here in the shell. Electrons have negative charge, right? So protons are positive, neutrons are zero, and electrons have a value of a -1 value. And so elements are balanced in charge. They have no charge because the electrons and the protons cancel out those charges. Okay? So we can change different parts of an element, or at least nature can do this, and we result in some variations of elements. If we, for instance, want to take away an electron from this orbital, we can pop that out. That leaves an excess positive charge in the nucleus, and we have a positive ion. Okay? However, in some instances, we can bring the electron back. I'll go ahead and erase this. You can add in an electron, sometimes more than one. So let's say I added an electron here, add an electron there. They both have a negative charge. So now this particular atom has a surplus of negative charge, so it has a 2- charge. Okay? So we call that an ion. These are summed up on the next slide. Okay? An ion. Now, in the nucleus, we can also fuss around a little bit with what's in the nucleus. And if we take one of these neutrons and remove it, this happens in by several different methods, but we're actually not removing it as much as we're just changing it from a proton to a neutron, and or kicking out. In some cases we kick it out. If we remove just a neutron, we create something called an isotope. Hold on a second, let me just erase that. We create an isotope. The isotope is an element that has additional neutrons or is missing some neutrons. Okay? And this brings us to an important point that I want to make, is that the number of protons, okay, which we also refer to as the atomic number, the atomic number, that defines the element. Hydrogen must have 1 proton. Helium must have 2. Lithium must have 3. By definition, if you change the protons, you change the number of protons, you change the element. If you change the neutrons, you create an isotope. And if you change the electrons in the system, okay, you create an ion of sorts. Alright, so most of that is summed up here, okay? Especially the important parts. We'll come back to isotopes when we need to. Ions, okay, atoms, and atomic number. Those are some critical definitions. Atomic weight is less important for us. That's the average weight of all the different isotopes for a particular element. So in some cases, for instance, we have oxygen 18 and oxygen 16, and they exist in nature in different proportions. So let's say 16 is 60% of all oxygen is that, and 18 is 40%. 18 is actually heavier than 16. Okay, it's got the same number of atomic number. Okay, so the atomic number for oxygen is 8. But oxygen 18 has 2 extra neutrons in it. Okay, so it actually has 8 protons and 10 neutrons, where oxygen 16 has 8 protons and 8 neutrons. This means that oxygen 18 is a little bit heavier because it has an extra 2 neutrons in it. And so that if we want to know what the weight of oxygen is, we don't usually worry about the isotope. It's the weighted average of both of these together. So this is why we don't really talk about it too much in this class. It's not going to come up. Okay. Now, atoms are going to get together, and when they get together, we have the potential to make molecules, and molecules can make minerals. Bonding comes in several varieties. We have interatomic bonds, and that's what I'm going to show you here for a particular mineral, which is halite. Okay? That means between atoms, the atoms are going to get together. And then we have intramolecular bonds, which occurs between molecules. Okay? So in this case, I'm going to talk about ionic bonding. It's one of 4 main kinds of bonding. We'll not cover them all. But the basic idea here is that in ionic bonds, we have an outer shell, and that's where bonding takes place. The outer electron shell, where the outer electrons exist. In both of these atoms, this is sodium and this is chlorine. If we take this and pop it off, get rid of it, we give sodium here a positive charge. Okay? And I'll just point out in this has a mistake. This is the cation on this side, and this is the anion on the right hand side, just down here at the bottom. I'm highlighting an error it's on my figure, but in the book's figure, or a book figure, not necessarily your book's figure. Anyway, we lose an electron. It gives the overall charge based on the number of protons in the nucleus positive. And then here in chlorine, it can pick up an electron from somewhere. So electron comes into chlorine, fills in this last little electron shell here, and ends up giving it a negative charge. Now, we have 2 objects, sodium, chlorine. One is, they're both ions, and they're oppositely and equally charged, so positive 1 and a negative 1 on the other side, which means they can get together. Okay. So, in general, what can we say about bonding? It doesn't happen or has very little to do with the nucleus of an atom. It is primarily tied up with the electron cloud, okay, or is driven by the changes in the electron cloud around atoms. Alright, so that ends for the summary or the chemistry overview. The next step will be to talk a little bit about the classification of minerals, and we'll look at both the chemical and the structural classification.